All right. Good morning, folks. Let's go ahead and let's get started with the lesson for today. And I want to just go ahead and let me start my timer actually. And that was then stay on track here. But I want to pick up with where we left off on was it Friday, Monday, what's today, Tuesday, Friday of last week. No, today's Wednesday. Um, Monday of this week. So I want to go ahead and I want to pick up with that discussion and hopefully try to get through the discussion of the ionic reactions. We'll do the Lewis dot structures, and then we'll continue on with the that discussion. Okay, so let me go ahead and let me share my screen with you here, and let's take a look at what ions are. Okay, so we talked about ions then as being atoms that have a charge to them. Okay, so the atoms can either have a positive charge or they can have a negative charge, depending on whether the atom picks up an electron or loses an electron. Okay, I'm going to assign a PhET lab for us to do our first PhET lab. I'm going to try to get you started on that maybe tomorrow if we can. So I'll let you know at the when I meet you tomorrow morning. I'll let you know how far we get today, and then I'll post a PhET lab for you, and then you can get started on the PhET lab for hopefully Thursday. If not, then you'll do it on Friday. Okay, so we'll talk about that. But just keep in mind then that when we talk about these charged atoms, what's changing then is the number of electrons. Okay, so when an ion is formed that is a cation, that positive charge comes as a result of losing electrons. An anion, when it forms, the charge results from acquisition, picking up an electron. Okay, so with that said, when ions do form, the reason why they form is that they achieve a more stable state. The neutral atom is not always the most stable form of an atom. We're going to see that some the neutral atom sometimes is not the most stable state. Now, some atoms are very stable. Some elements in their neutral form are very stable, but a lot of them are not, and so they want to change. And so, forming the ions, losing or gaining an electron will allow them to achieve a more stable state. And what that stability looks like in terms of electron configuration, we're going to talk about that today as well. But ions typically don't exist in isolation from one another. I mean, with the exception then of when we talk about solutions, but ions tend to form and then they aggregate. They come together in order to continue to be stable. So the stability then is a result of not only losing and gaining an electron and obtaining a more stable electron configuration, but also in interacting with ions of the opposite charge. Okay, that even brings more stability to the atom itself. So we're going to talk about ionic compounds, and I did mention, I think it was on Friday of last week, then yeah, when we started this, I did mention then that you got to make sure then that you start memorizing that table in chapter 9. I think it was table 9.2. Make sure you start memorizing the formulas for those polyatomic ions, because we need to learn how to name these new substances, these new ionic compounds, and we have to be able to represent them as well. So we're going to talk about that in this chapter. We're going to talk about how we represent and how we write out their names for simple, what are called binary ionic compounds. And then we'll wrap up this chapter by talking about how metal atoms, okay, how metal compounds, they're able to get together and form a a solid. Okay, so we'll talk about that, but I think I did mention then also with these metallic bonds, the discussion, a better understanding of metallic bonds is a little bit above the level of this class. We talk about it quite a bit more in AP chemistry. So I'm going to introduce then a very simple explanation, simple way that we can understand how metals bond together. But I'll leave a more detailed discussion of that until AP chemistry for those of you who are going to be moving on to that class. Okay. All right. Very good. So let's go ahead then and let's take a look at these ions. Okay. What I want to do then is let's talk about how these ions form and then how we represent these ions first. Okay. All right. So first and foremost, what we need to make sure we understand then is that whenever we talk about ionic compounds, and actually whenever we talk about how um, compounds form, whether they are ionic compounds that we'll study in this chapter, or whether we're talking about molecular compounds, which we will talk about in the next chapter, whenever compounds form, it's the interaction of atoms with other atoms. And that interaction takes place as a result of the exchange or the interactions of electrons. And more specifically, it's going to be the interactions of the electrons that are furthest away from the nucleus, what we refer to then, remember, as the valence electron. So let's make sure we keep this in mind then, that for valence electrons then, those are the ones that that we learned about. Those are the ones that are critical in determining the chemical and the physical properties for the most part, of elements. Okay? And so if you take a look at phosphorus then, phosphorus here has these electrons out here. You have 1, 2, 3, 4, and 5. These are the 5 valence electrons. Again, these are the electrons that are furthest away from the nucleus. We refer to these as the valence electrons here. And so these are the valence electrons. And what we remember then, these electrons are going to be situated then. So if you take a look at this one, this is in the third energy level here. So you have 3s2 and 3p3. So 2 of these are in the s orbital, and 3 of these are in the p orbital. So the s orbital is filled, but the p orbitals here are going to be partially filled. In the p orbitals then, what we're going to see then is that these electrons, and this is going to be an important discussion here that you need that we'll need to understand. Okay. So with the 3p orbitals here, let's go ahead and make sure you understand this. These 3 electrons here are going to spread out. Okay? These 3 electrons here, remember, according to Hund's rule, they don't want to share space. They're going to spread out. So we have then 3 electrons that are not paired with the, so these are the 3p electron, 3p orbitals. And then with the s orbital, which is lower in energy here, you have 2 electrons, and they fill in that space. So yes, you have a total of 5 electrons that are valence electrons. So we have 5 valence electrons, and you do need to make sure you keep that in mind. But also what you need to make sure you keep in mind then is that we have 1 pair of these 5 electrons, 2 of them pair up, and then the other 3 spread out. We have 3 unpaired electrons. So we so first of all, and so let's make sure we are clear on this. These are valence electrons because these are electrons in the highest energy level. Okay, and furthermore, then, and we can obtain that because phosphorus then is in group 5a, and so we know then that it has 5 valence electrons. Okay? After that, what you need to make sure you understand, and what make sure you remember then, is that the 5 of the 5, 2 are in the 3s orbital and 3 are in the 3p orbital, which means then you have 1 pair and 3 unpaired. That is going to be critical as we move forward. Not only do we need to make sure we can recognize the valence electrons, we need to make sure we are able to identify how they interact with one another. So for phosphorus here, we have 2 that are paired, 3 that are unpaired. That's how they interact with one another. Okay? So let's go ahead and let's take a look at calcium then. And so calcium then has 2 valence electrons here. So you have then 1 and 2 here. Okay. And so with that said, then these are found, calcium then, these valence electrons here. Let me go ahead and do this here. You got 1, 2, 3, 4. So we have then these valence electrons for calcium, okay, are found in the 4s orbital, and they're both in the 4s orbital. And so what does that mean then in terms of how they interact with one another? These 2 then are paired, and that's as simple as we can get it. So these 2 are not separate the way that we see it here. They're actually paired up in the 4s orbital right there. Okay. Now, this is going to be important here, you guys. This is going to be really important when we start talking about the Lewis dot structure. Okay, so the Lewis dot structure, when we write these, and we'll see this in just a moment, when we write these, we have to identify the electrons that are paired and the electrons that are unpaired. So with calcium here, both of those electrons are paired in the 4s orbital. Okay, and again, we can get that because calcium is a 2a. Sorry, it's in the 2a. It's an alkali earth metal. So it's a 2a atom. Okay. All right. So make sure you're able to do this. And I'm going to emphasize this. I'm going to do this a little bit more. We're going to go over this a little bit more as we start talking about Lewis dot structures. But you really got to make sure then that you're able to identify how many valence electrons each atom has, okay, as we go forward with this. And then also you have to be able to identify the electrons that are paired, the valence electrons that are paired, and the valence electrons that are not paired. Okay. All right, so let me go ahead then and let me save this and let's continue on with this. Okay, so with that said, then these valence electrons, like I pointed out, they are the critical electrons. Now, that's not to say that the other electrons, what we refer to core electrons, are unimportant. No, they are important, but in terms of how atoms interact with other atoms, that is, in terms of the bonding, okay, it's the valence electrons that are critical. Okay, so that's why we focus in on those. Okay? All right, so with that said, then the elements in each group, remember we talked about this. They all have similar, so within each group, each column, they all, for the most part, behave very similar to one another, okay, because they have the same number of valence electrons. They have a pretty similar electron configurations, especially when we talk about valence electrons. They have that in common. And that's the reason why they will behave very much the same. Okay, so within a group. Okay, whoops, sorry. Okay, and so the number of valence electrons, just as a quick reminder, then, it's going to correspond to the grouping of the group number, especially if we are using the American or European numbering system. Make sure you keep that in mind. That's the numbering system where you have a number and a letter. Okay, so make sure you keep that in mind as well. Okay. So with that said, let's practice this a little bit. Okay, and let's take a look at each one of these. We talked about each one of these here, and what we're going to do then is we're going to go ahead and identify the number of valence electrons for each one of these atoms. But further, what I'm going to do then is we're going to decide then whether the electrons, these valence electrons, are going to be paired or unpaired. Okay. All right. So let's go ahead and let's go through this, and let's go through these 4 atoms here. So potassium is an alkali metal. It's a 1A metal. So let's go ahead and write that down. It's in group 1A. We know that about potassium. Carbon is a 4A element. Magnesium is an alkaline earth metal. It's a 2A, and then oxygen then is going to be a 6A element. So I want to make sure you are aware of that, because we can use this to identify the number of valence electrons. So we know then that potassium is going to have 1 valence electron. Okay. Carbon then is going to have 4, based on the group number, 4 valence electrons. Magnesium is going to have 2 valence electrons based on the group number again, and then oxygen is going to have 6 valence electrons. Okay, so hopefully everyone's able to identify that fairly easily. Okay, I hope that's not going to be an issue, but I want to go ahead and I want to expand upon what we just talked about and be able to identify whether these electrons then are going to be paired or unpaired. We need to make sure we are able to do that. So in order to do that, what I'm going to do is let's go ahead then and let's write out the electron configurations for each one of these. And I'm going to use the noble gas configurations because, again, the core electrons, we don't really need to focus in on. We want to focus in on the valence electrons. And when we write out the noble gas configuration, that's what we'll get. We'll get an idea of the electrons that are furthest away from the nucleus. Okay. All right, so potassium then, it's going to be noble gas configuration. It's going to be argon, okay, and it's going to be 4s1. Okay. Carbon then, it's going to be helium, and it's going to be 2s2, 2p2, and then magnesium then is going to be neon, and 3s2, and then oxygen is going to be then helium, 2s2, 2p4, right? So there it is. 1 valence electron, 4 valence electrons here, 2 valence electrons, and the 6 right here. So we've accounted for all those. How do we determine then whether these electrons are paired or unpaired? What I would suggest you do first, and this is something that you probably should do initially because it will help you kind of figure this out. For each one of these orbitals, I would suggest you draw out the boxes. Okay, so there is the 4s. Okay, let's say that this is the 4s orbital right here. So 4s orbital. Remember, s orbitals only have one shape, so that's only one space in which the electrons can go. And here then, this 1 valence electron right here is going to go into that 4s orbital. Okay? And so therefore, potassium then has 1 unpaired electron. Pretty straightforward, not that simple. So that 1 valence electron is completely unpaired. Okay, there's nothing paired up in here with that. Okay, all right. Now let's go ahead and let's take a look at carbon then. Carbon has electrons in the s orbital and the p orbital. So we're going to go ahead and we're going to draw both of those. Okay, so let's draw both of those. So let's go ahead and draw out the s orbital. There is the s orbital, and then we'll draw out the 3 p orbitals as well. because we've got to indicate where the electrons are located there. Okay, so here is the 2s orbital, and these three here are the 2p orbitals. Okay, so there's three of those. All right, so fill it in. We got 2 electrons in the 2s. There it is. And then we have 2 electrons in the 2p. Now, these 2 electrons here will not share a space. Remember, Hund's rule tells us that if the electrons can spread out across a set of orbitals, it will. Okay, so these 2 will be unpaired. So therefore, carbon then has one pair of electrons. So we have 1 pair, and we have one pair of electrons, okay, and 2 unpaired electrons. Okay, so there it is. We have a pair right here, and these 2 are unpaired. Again, this is going to be critical in your ability in just a moment to write out Lewis dot structures. So you need to be able to identify which of these valence electrons here are paired versus unpaired. Again, the group number just tells us how many valence electrons there are. But it doesn't help us in terms of how to identify which electrons are paired or unpaired. And so what we're doing in red here, I'm hoping at some point you can do this mentally. You can just do it in your head, okay? But until you get to that point, I would, again, highly suggest you draw out these boxes and then fill in them, okay? All right, with magnesium then, let's go ahead and let's take a look at this. Magnesium has electrons in the 3s orbital here. So let's go ahead and draw out that box. There's the 3s orbital. Okay. All right, so there's the 3s orbital, and there's 2 electrons, and both of those are going to fit into the 3s orbital. So therefore, magnesium then has 1 pair of electrons and 0 unpaired electrons. There are no electrons that are unpaired. Okay, so 1 pair and 0 unpaired. Okay. All right, let's do that. Let's take a look at oxygen. Oxygen has electrons in the s orbital and the p orbitals. So let's go ahead and draw those out. Okay, so you have then the s orbital here, and then again you have your 3 2p orbitals. There they are. Let's go ahead and fill it in then. So you have then the 2s orbital here, and then you have the 2p orbitals here. 2 electrons in the 2s orbitals. So you have 1 pair right there. Okay, and then you have 4 electrons here. So let's go ahead and fill this in the p orbital. You have 1, 2, and 3. The 4th one must share one of these spaces here. Okay, and so with oxygen, then, if you take a look at this, you have 2 pairs of electrons. So these 2 here, that's 1 pair. This is a 2nd pair right here, and then you have 2 unpaired electrons for oxygen. Okay, so we count, this is 1 pair right here, and this is a 2nd pair right here, and you have 2 unpaired. And again, you have to make sure you're able to do that, because in order to write out the Lewis dot structures, that's what we're going to do. So we'll practice that a little bit more in just a moment. Okay, so please, though, make sure tomorrow, if you have any questions on this, stick around, and then we can go over this together. Okay, so please make sure then that you can do this. So if you cannot, please make sure, again, like I said, tomorrow, after I dismiss you to go watch your video, watch the lesson, stick around, and we'll go over more of, we'll do more of this. Okay, so please make sure you get your questions answered about this. Okay, but let's continue on. Okay, let's continue on, and let's talk about how we can represent these atoms then. Okay, so there is a method that we can use to help us then to kind of simplify how we can see, how we can view these electrons, and how they will be exchanged, and how they interact with one another to form these bonds. Right. So a method known as drawing out the Lewis dot structures. And Lewis dot structures, what they do basically is it's a symbolic way to represent an atom with their valence electrons. Okay. And then what we do with the Lewis dot structures, then you'll see in just a moment, we can use it to see that and trace how these electrons move around as the bonds form. And so let's learn how to draw these Lewis dot structures first, and then we'll be able to use them in order to identify or to show how these electrons move in order to form these bonds. Okay? So Lewis dot structure is made up of basically two parts. The symbol for the element itself, okay, that is the letter or the 2 letters that represent the element, and then dots. And the dots then will represent then the electrons, okay, in an atom, okay, for an atom. And so those are the two parts. Those are the two parts of the Lewis dot structures, which you see here as well. So for the for fluorine here, okay, so for fluorine, you see then that there is the symbol for fluorine. So there is the symbol. Okay, so again, for Lewis dot structure, it's going to be two parts. It's going to have the symbol for the atom, okay, and then we see that also for nitrogen right here. So nitrogen, there's the symbol for nitrogen. Nitrogen's symbol is an N. Okay, the letter N represents nitrogen. So there's the symbol for nitrogen. Okay, and then if you notice, there are these dots. There are the dots that surround each one of these atoms here. And you notice there are all the dots. Okay, and those represent the dots. Then represents the valence electrons. Okay, and if you notice, there it is. Fluorine is a 7A. It's a halogen 7A element. So you have 2, 4, 6. There are the 7 electrons for fluorine, and nitrogen is a 5A element. So if you notice here, you have 2, 3, you have 5 electrons here. Okay, so there it is. So the two parts of a Lewis dot structure, the symbol and the dots. Now, what you should notice is that we place the dots around. We place the dots around the symbol. The sphere here is just there to represent it. We're not going to draw the sphere. We're just going to draw the letter. Okay. But if you notice in the dots, we put around the symbol. Okay. Then what you should notice here also is that we have pairs of electrons, and then we have unpaired electrons here. With nitrogen, we have one pair. These two are paired up, and if you see, we draw it very distinctively paired up, and we have 3 unpaired electrons. We have to be able to represent them that way. Okay. And here we have them with fluorine. We have 3 pairs. Okay, so 6 of those electrons are all paired up, and 1 of the 7 is unpaired. Okay. And so when we draw these Lewis dot structures, we really have to emphasize then the pair versus unpaired electrons. Okay, so make sure you keep that in mind. Okay. All right. So let's go ahead and let's practice this. Let's go ahead and let's take a look at this, and let's see how we go about drawing these here. Okay, so save this, do this up, and let's practice with the 5 elements that 5 atoms that we just dealt with. Okay. All right. So with potassium, then I'm not going to write it all out again, but let's go ahead then, and I'm going to indicate then the noble gas electron configuration. Let's go ahead and start with that again. Okay, so potassium then, it's going to be argon. Okay, and it's going to be 4s1. Now, I want you to recall that we did this. This one electron is an unpaired electron, and if you need to, please go back and review the previous a couple slides back, and to show you to see how we know that this is an unpaired electron. Okay. All right, so we have potassium. It's an unpaired electron, and so when we draw the Lewis dot, when we write out the Lewis dot structure for potassium, we're going to start out then with the letter for the symbol for potassium, which is going to be K. Okay, so there's the symbol. It is one unpaired electron, so we're just going to use 1 dot to represent that. Okay. Now we do not. If you notice here with the symbol for potassium, okay, what we do not do then is we don't indicate that electron is in the 4s. We don't write that in for the Lewis dot structure. We only indicate that there is one. There is one electron, one valence electron. You have to remember, okay, from this symbol here, from the Lewis dot structure, you have to actually remember that this one valence electron is in the 4s orbital. You have to actually remember that. Okay, so but you do not indicate that in the symbol itself. Okay, all right. So there's the Lewis dot structure for potassium. Let's go ahead and let's do the same thing for carbon. Okay, so again, carbon, the electron configuration for carbon then is going to be helium, okay, 2s2 and 2p2. Okay, so with carbon, remember we said then that we had 1 pair, that these 2 electrons here, okay, 1 pair, and we have 2 unpaired. Okay. All right, so let's go ahead then, using that, let's write out the Lewis dot structure for carbon. So with that said, the symbol for carbon is C. We're going to have 1 pair, so I'm going to go ahead and write that in very distinctly. Those 2 are going to be paired up, and then these 2 here are going to be unpaired, and I'm going to write them on the side right here. Okay, so that's going to be the Lewis dot structure for carbon. What do we have to indicate here? Is we have to indicate the 2 electrons that are paired. Okay, there's our pair right here, and the 2 that are unpaired. Now, Doesn't matter where you put it around the carbon, okay? It's just make sure then that you have then a pair and unpair. So you can go ahead and you can easily have put the pair here in the back behind the carbon to the left and have the unpaired at the top and at the side. Again, it doesn't matter where you put these electrons, these dots, doesn't matter where you put these dots, both are equally valid. It's just, you got to make sure then that you have one pair and one unpaired. So it doesn't matter where you put the dots around the symbol for carbon, you just have to indicate that which ones are paired and unpaired. Okay, so both of these are equally valid. Okay. All right, let's take a look at magnesium. Okay, so magnesium then has the electron configuration of neon, okay, and 3s2. And we recall again, these two electrons are paired, so we have one pair and no zero unpaired. So that's what we have for magnesium. Let's write out the Lewis dot structure for magnesium. The symbol for magnesium is going to be Mg, okay? And then I'm going to put the two pairs right there. And if you notice then, I put it to the left, but again, it doesn't matter where you put those dots, you just got to make sure then that they are paired. What you cannot do though, is you cannot write magnesium and have two dots that are separate. That you cannot do because the electrons for magnesium are paired. So that is not a valid structure for magnesium. You have to have them paired. So whether you put the two dots here to the right, to the left, on top or on bottom, that doesn't matter. You just got to make sure that they are paired. So that's the Lewis dot structure for magnesium. Okay. All right, let's go ahead and let's take a look at oxygen. The last one, helium then. Okay. And we have then 2s2 and 2p4. Okay. All right. So let's go ahead and write out. So this then is you have one pair. Remember, these two are going to be paired. So we have one pair, and I'm sorry, two pairs. I'm sorry. We have two pairs here. We have a pair here, and then we have a pair in the 2p orbital as well. So we have two pairs of electrons and two unpaired electrons. Okay. All right. So let's go ahead then and let's write out the symbol for oxygen. Here, oxygen is an O. So we're going to put the two pairs. Okay, I'm going to put them one of those pairs I'm going to put to the left, and one I'm going to put on top. And then the two that are unpaired, I'm going to write them. I'm going to draw one to the right and one at the bottom. Okay. And so that is the Lewis dot structure for oxygen. Again, where you place these dots doesn't really matter. Okay. But what does matter then is that you have two pairs and two that are unpaired. Okay. So that is how we write the Lewis dot structure for each one of these atoms here. Okay. All right, so let me go ahead then and let me save this and I'll post it for us as well. Okay. Let me go ahead then and I'm going to ask you, let's take a look at number 14 in your problem set. Okay, let's take a look at number 14 in your problem set. And what I would like you to do for these four atoms, okay, on your paper, okay, and then please make sure you submit your work at the after you finish watching the video. But take about 3-4 minutes to try your best with the Lewis dot structures for these four atoms here. Remember, write out the symbol and indicate and then draw an equal number of dots for the number of valence electrons that each one of these atoms have, and then make sure then that you either pair them up or write them out unpaired depending on how those electrons situate themselves across each one of those orbitals. Okay, so take about 4 minutes. To write out the Lewis dot structures for these four atoms here, and then when we come back together again, I'll work them out for you, and then compare your answers to what I give you. Okay, 4 minutes, folks. Okay, hopefully you had a chance to work through that, you guys, and try your best with it. I don't think it's that difficult, but you do have to practice this. Okay, so let's go ahead and let's take a look at each one of these. So I already gave you the symbol for each one of these elements here. We just need to make sure then that we write them out. Okay, so let me go ahead then, and I'm just going to write it to the side here really quickly. All right, so beryllium. First thing we go, again, if you need to do this mentally, go ahead and do so. But what you want to do then is indicate then write out the electron configuration for it. So beryllium then is going to be helium 2s2. These two electrons here are in the 2s orbital and an s orbital, so you know that they have to be paired. And so if they are paired, we can go ahead and write out the symbol for beryllium. I'm just going to write it to the this side here, so we have both sides. And then we can go ahead and make sure then that we write out the pairs right there. Okay, so that is the symbol for beryllium. That's the Lewis dot structure for beryllium, and the two dots have to be paired. Okay. Again, writing out the electron configuration for these atoms, you don't have to. If you really need to only focus in on the valence electrons here. But if you need to write it out, please make sure you do so. Okay, and I'm going to continue to do so for right now. Okay, just to get you to think about this. But again, you don't have to. Okay, all right. For fluorine, then it's going to be helium, okay, 2s2 and 2p5. So we're going to focus in on all 7 of these here. Okay, and so again, if you need to, hopefully you see then that these 2 electrons here are paired, whereas of these 5, 4 of them will be paired, okay, and then 1 will be unpaired. Okay, so hopefully you see this. So here we have 1 pair up here for beryllium. Here we're going to have 3 pairs, okay, and 1 unpaired. And again, if you are not quite sure how we were able to get this description here of these electrons, please make sure tomorrow, stick around after I take roll, and then get some help with that. Okay. All right. So with fluorine, then the symbol for fluorine is going to be F. And so when we write out the Lewis dot structure, we have to indicate the 3 pairs. So we have 1 pair right there; those 2 go together. A second pair here; those 2 go together. A third pair right here; those 2 go together. And then we have 1 unpaired electron. So that's going to be the symbol for fluorine, and we saw that already. Okay, so let's go ahead and do that. Okay. All right, let's go ahead and take a look at sodium then. Sodium then is neon, okay, and 3s1. Okay. This 1 electron then is going to be unpaired, so it has 1 unpaired. Hope you can recognize that as well. Okay. And so when we go to write out the symbol for sodium, which is Na, okay, we're only going to place 1 dot next to the symbol, and that then is the Lewis dot structure for sodium. Okay. All right, let's go ahead and let's take a look at phosphorus. And phosphorus, and let's look at the electron configuration for phosphorus. It's going to be neon, 3s2, 3p3, and we did this analysis earlier on. We have these 2 electrons here are going to be paired, so it has 1 pair. And these 3 here are going to be unpaired, so you have 3 unpaired electrons. Okay. And so let's go ahead and write out the symbol for phosphorus, which is going to be P, making sure then that around here we place 2 dots that are paired. Okay, so we have 1 pair there, and the remaining 3 are going to be separate from one another, and they're going to be unpaired. Okay. All right, so that now is the Lewis dot structure for phosphorus. So the homework, I'll assign the homework for tomorrow, but the homework then is going to give you an opportunity to practice writing out these Lewis dot structures a little bit more. But please, you got to practice this in order to get this done correctly. Especially, and again, I think in the past, what most folks have the hardest time with is trying to figure out then pairs versus unpaired electrons. What I highlighted in red right now is what you really have to make sure if you are not quite sure how we get these. Go back and review that or combine seeding, but that's been the main issue. Writing out the Lewis dot structure itself, not the beginning issue. You got the symbol, you got the dots. Okay, it's trying to figure out whether the dots are paired or unpaired. That at least in the past, students have had some issues with. So please make sure then that you review electron configurations here in order to understand, and then how the orbitals fill in order to determine then which electrons are paired and which electrons are unpaired. But let's continue on then, and let me go ahead and clear this out here. Okay, and let's take a look at why then atoms choose to form ions. Okay, now if you recall, we talked about this then when you looked at the noble gases. Okay, so when we looked at the noble gases, which is group 8A. Okay, so with group 8A. We said that the noble gases, first and foremost, have completely filled s's and completely filled p orbitals. Okay, so this is the configuration that you should notice then for noble gases. The s orbitals are completely filled with 2 electrons, and the p orbitals are completely filled with 6. So every electron is paired. Make sure you understand then that what we have here for noble gases is that all electrons are paired. We have then all electrons are paired. So they are all sharing that space. So for the noble gases, okay, all electrons are going to be paired. That means that you have a completely filled, okay, completely filled S and completely filled P. So the valence electrons, okay, they represent then a situation in which every orbital is completely filled. And if you notice it, you'll have 8. Okay, so whenever you have all S orbitals and all P orbitals completely filled, then you're going to have 8 electrons, and that represents them. And if I may just finish up here, that represents then a very stable situation. Because remember, the one key feature of noble gases, the one key feature about noble gases is that they are very stable. They are very stable. They have a great deal of stability. That's why remember when we talked about electronegativity, the noble gases don't even have a value. We don't even calculate a value for the electronegativity of noble gases because they don't want to add any more electrons. And it's really difficult to get noble gases to give up their electrons as well. And if you notice their ionization energies are very, very high. So noble gases are very stable. So this configuration here where you have 2 electrons in the s orbital and 6 electrons in the p orbital, that represents a high amount of stability. It's very stable. Okay? And so atoms, again, remember, want to become stable. And so in order to become stable, atoms then will either gain or lose enough electrons in order to get 8 in their highest energy level. Okay? So they will gain or lose enough so that what they will obtain or what they are left with will be 8 electrons in the valence in their outermost energy level. Okay, and so that's where we'll pick up with on Thursday, on Thursday's lesson. So we'll pick up with that, and then we'll talk about how we can apply this octet rule in order to determine then whether an atom will gain electrons or an atom will lose electrons. Okay, and so we'll talk about that, and we'll pick up with this discussion on Thursday. Okay. All right, very good, folks. I'll see you in class tomorrow, so please make sure you stop by. You got to stop by first so that I can take roll, and then inform you of any administrative, any messages that I have to send out to you. And so we'll talk about that. And then after I take roll and then we deal with all the administrative stuff, you will go and you'll watch the video for Thursday. But remember, I will be available during that class period. So you stick around after I take roll, and then I can answer any questions that you have about today's video. Okay. All right. So I will see you tomorrow in class, and then we'll pick up with this discussion in the video tomorrow. Okay. Have a good one, guys. I'll see you.